2 lectures ago, I tried to convince you about the fact that you already knew. The fact was that light behaves like a wave. And the last lecture, our head TA, Greg Dellinger, gave you a beautiful lecture, and he tried to convince you that light behaves like a particle. And then at the end, he married it with the de Broglie relation. So what he has shown to you is if you take light and you would put it through a series of filters where you cut it always in half and in half and in half, a quarter, 8, 16, 30 seconds, and so on. You do this until you can't do it anymore. You get one blip of light. And actually, you can see this blip of light. In a very dark room, if you do this, you see every now that blip of light. And this blip of light is called a photon. That's the smallest package that light can travel as. Okay? It's a photon. And the energy of this photon is h, that's the Planck's quantum, times nu is the frequency of that light. So now we have established that light comes in packages, but there is a smallest unit of package, which is called the photon. And this we can see is a particle, essentially. And then he has demonstrated to you the photoelectric effect insofar that you have a metal. And this is what Einstein, he didn't get the Nobel Prize for metal, but Einstein got the Nobel Prize for discovering the photoelectric effect and explaining it, not for the relativistic effect or for relativity. Many people think he got the Nobel Prize for this. Of course, he would have deserved it, but he didn't get it for that. So if you imagine you have a metal, and the metal has nuclei and electrons, and the nuclei hang on to these electrons. And that's what we call binding energy of the electrons. They are bound in that nucleus, in that atom. So they have a binding energy. The nucleus hangs on to them. Now, you could imagine you need to get an electron off this metal, you have to rip it off. So you need to take energy. And so we can provide this energy by using light. But we can't use just any light of any frequency, of any energy. The light has to have that energy which is at least as big or bigger than the energy as the nucleus is hanging on to that electron. That's called the binding energy. So what we do is, so if you, for example, you did an experiment, he had red light, this had relatively low energy, nothing happens with this specific metal. Then he increased the energy, and he had green light, and booms, there was an electron dislodged. And so the light has h times nu, you can calculate this, and the kinetic energy of that electron is essentially the energy of your light minus the work function. That's essentially the binding energy that you have to overcome. How the nucleus hangs on to that electron. You need to be bigger than that force that the nucleus extends to that electron to get it out of the atom. So with this you have, we call this the work function, you have h nu minus h times nu 0. So there is a certain energy that you need, minimal energy, to dislodge that electron. So if you do, and if you have a larger energy than you need to dislodge this electron, the rest of the energy is transferred to that electron as kinetic energy. So you can do the same thing with blue light, which has a higher energy, and with this, the kinetic energy of that electron will be larger. Okay? Because you need only a certain energy to dislodge it, and the rest of the energy is transferred as kinetic energy. So we have seen that light, and I'm repeating here now, is a wave. And now we have seen that light is also a particle that comes in smallest units in quanta. And maybe to give you the example, if you look at atoms, for example, let's see we have a bunch of oxygen atoms. Oxygen has 8 protons, okay? So we cut the amount of atoms in half, we cut it further in half, cut it further in half. At the end, we have one oxygen atom. If we cut that oxygen atom in half, we don't have oxygen anymore. What would we have? What would we have? Beryllium. Okay, is that right? Half of 8 is 4. Yeah, we have beryllium. Good. Okay. So that's not oxygen anymore. So the smallest unit of an atom is the atom itself. And the same thing is with light. You can only cut it till it comes to the smallest quantum. That's the light itself. That's the quantum itself. So as we have seen, the light has a wavelength. It travels with the speed of light. But it also has a particle. And any moving particle has a momentum. Momentum is P equals mass times its velocity. And kinetic energy is 1/2 times the mass times the velocity squared. So momentum and kinetic energy is also related. So de Broglie came along and rectified this. He said, I can calculate a momentum for any wave, because the wavelength is related to is inversely proportional to the momentum over to h over the momentum. Okay, h is the Planck's quantum, and so I can calculate. That means you can, for any moving particle, you can calculate a wavelength, anything. If this makes sense, that's a different story, and that's what we're going to talk about it today. So you can calculate a wave. If you know the momentum of that particle, you can calculate the wavelength. Fine. If you have a wavelength, you can calculate the momentum as a particle. You can do this vice versa. And there's this duality between wave and particle. Is it a particle? Is it a wave? It's a particle. So with light, we have explained this now. Now we're going to go and talk about the electron. And you know electrons, they have mass, they have a charge, they are a particle. They have about the thousandth of the mass of a proton or a neutron. We know electrons are particles. Now, if I take an electron gun here and have the two-slit experiment, and I shoot electrons here, they go through here and they go through here, and I get this kind of interference pattern. What does this tell me? What does it tell you? Is this a particle? Does it behave like a... Would the particle behave like this? No. It shows an interference pattern that the darn electron behaves like a wave. But we know it's a particle. But it behaves like a wave, otherwise it wouldn't show us this interference pattern. So the wave goes through here, up, down, up, down, up, down, up, down, up, down, up, and through here, up, down, up, down, up, down, up, down, up, and they have constructive interference, and we have a high intensity here. It's not light at the moment, it's the intensity to find that electron. If we make it that it flashes light, then it would be high intensity. So if we have constructive interference, there is high intensity. Of course, it goes, you know, you have shown this. This has to travel a whole wavelength longer than this one here. And if you have destructive interference, that means peak and valley, or crest and trough, you have destructive interference, there's nothing. So the probability to finding the electron here is 0. 0 here, 0 here, 0 here. So now comes the crazy part, and welcome to the quantum world. If you use one electron, just one electron, it shows the same pattern. It interferes with itself. Okay, this is not part of that lecture here that I explained to you how this works, but it interferes with itself. And I said to you the last time that I'm going to send you the video on YouTube of Dr. Quantum double slit experiment. It will explain this to you again in a much more comical and entertaining way than I can provide to you. All right, so with this we know that that electron, which we know is a particle, behaves like a wave. All right? So now it's obviously not that particle on a string, which is the Bohr model, which you learned, some of you learned in high school, because the professor sort of did not advance his knowledge a little bit. He should have taught you a little bit of quantum, you know. That Bohr's model is totally wrong. There's something right, the number of different energy levels. This is right. But the Bohr's model was before quantum mechanics. So we look at electrons in terms of quantum mechanics. They are quantized because they are waves and they are particles. And with this we can say again, we can have a momentum is the mass, we know the mass of that electron and we know the velocity. So we say, we treat it like a particle, we can calculate the momentum. But we also know that it's a wave, which I have just shown to you. I didn't do the experiment because I don't have any electrons around here. No, not with me today here. And so you see, this is the way waves are characterized by the wavelengths, and particles are characterized by the momentum. And so what we do, you can describe this mathematically. You can describe waves mathematically, and you get a wave function. Don't worry, we're not going to get into wave functions too much. But you get a wave function that's a mathematical expression of a wave. All right? And we call it psi. And so if I square that wave function, then these negative lobes here go positive, and we talk about this a little bit more because it's easier to deal with. And this will show you the probability where you find that electron. The electron, if you square this, the electron wouldn't be here. It could be here, or it could be here, or it could be here, or it could be here. I know it goes past you at the moment, but you will get it, okay? So again, we can say I can calculate a wavelength for any electron, and I can calculate a momentum for any wavelength. I can a wavelength for any particle. All right. So this is the de Broglie wave-particle relation, which we have discussed. When we deal, anytime we deal with waves and particles, this relation holds true, given that the particles are small enough, that they are really quantum particles. So when do you know what is a quantum particle or not? So if you, for example, an airplane has mass and velocity. I have mass and velocity, I have momentum. I can calculate a wavelength. So I could calculate the de Broglie wavelengths. I could say this airplane behaves like a wave. Hopefully not, okay? It would be a pretty difficult ride in it. But this makes no sense, because quantum particles have certain conditions that we put on them. It can't be airplanes, it can't be trucks. And now, let's look at a couple of these quantum particles. We look at a photon, and this has 600 nanometers. It's given the wavelengths, and you can calculate the momentum. So photons, we know, are waves. 600 nanometer has a colored photon. You have an electron. That's what I've been talking about most of this lecture so far. You have an electron. It has 10 to the 5th meter per second velocity. So you have the velocity, you know the mass, p. You can calculate p, and with this you can calculate your wavelength. That's 6 nanometer. So that's pretty large, 6 nanometer. An atom, anybody remember the radius of an average atom about in nanometers? Anybody? 500 nanometers, 1 nanometer, a tenth of a nanometer? It's a tenth of a nanometer, okay? The average radius of a relatively small atom is a tenth of a nanometer. That's a good answer. So this is 10 to minus 10 meters. I told you this in the second lecture when I was talking about the nucleus and the relation of the atom to the nucleus in size, 10 to minus 10 meters. So that de Broglie wavelength is 6 nanometers. So if it would be the atom itself is 0.1 nanometer, so it's quite a bit larger, the de Broglie wavelength. So that means it's around that nucleus. It could be around the nucleus. So that's a reasonable wavelength, but we're getting there already sort of into an area where we have to be careful. If you have a sodium atom, you know the sodium atom? I just said it's a 0.1 nanometer about the radius. And this is a cold sodium atom. So motion and temperature actually is related to each other. And especially in this class, the faster a particle moves, the higher the temperature is. And if the particle doesn't move at all anymore, then we have 0 temperature, absolute 0. There's no particle in the world that doesn't move at all. We never ever reach 0 temperature. Okay? So this is how we understand it. You don't have if you measure very low temperatures, you don't have a temperature gauge which measures the temperature. You put it in, my 0K gauge. So you calculate the wavelengths, and from this you can calculate then the temperature. Okay? So, but it's just a sideline. So sodium, we said it's about a 0.1 nanometer, and the de Broglie wavelength is 0.06 nanometers. So that's a reasonable wavelength, which makes sense. It's about within an order of magnitude within the size of that atom. Now let's look at the baseball. Baseball is, I've been told, it's funny, it's measured in grams actually, it must be in ounces also. It's 170 grams. Baseball is an American sport. And you have to grow up with it to appreciate it. Unfortunately, I didn't grow up with it. I like to watch it, but I don't understand it, okay? And it seems to be a rather complex game, if you really need to understand. And you need to drink a lot of beer with it. That's how I like it, especially, okay? And so, many people, and this is the interesting thing, in this country, so that's why the United States are not that great in soccer. You have all the kids, the girls and the boys, they all play soccer. And they learn all this stuff. And when they are 13, then finally they start to playing football. And you lose all this talent. That's why America never is going to be world champion. Okay? You lose all this talent, unfortunately. Yeah? That would be quite something. But if you have so many people, maybe it will work out. You never know, statistically. So let's go back to science. Baseball. You have a baseball has a mass and a velocity. And the higher the velocity, the better the pitcher. I understand that. Okay? So, and we say 40 meters per second. I think this is about 100 miles, actually, if I would calculate this. 40 meters per second. So you calculate now the de Broglie wavelength. And you get a number of 6 times 10 to minus 26 nanometers. So this times 10 to the minus 9, this is 6 times 10 to minus 35 meters. This is so incredibly small. You cannot imagine this. There's nothing you can divide that small, actually. Okay? So this is nonsense. You can only use quantum particles and treat them as quanta. You can't use macroscopic particles, very large particles. They are not following quantum mechanics. So in this case, you have to just apply regular mechanics or regular physics, not quantum mechanics. Right? So you can calculate the de Broglie wavelengths of anything, but it has to make sense. So one interesting experiment, for example, is if you look at and many of you have done this, you have an optical microscope. And you look at a hair. A hair is about a micrometer. You look at the hair, you can focus the light that bounces off, the visible light that bounces off that hair, and you can see it. Okay, it reflects it, and you can see it. Because a hair is about 1 micrometer, and the light itself is between 400 and 700 nanometers, this 0.4 to 0.7 micrometers. So that's about the right size relationship, that object and the light that you bounce off. So it really can bounce off, because the wavelength is right, and you can visualize this. Now think about an atom. Let's think about an atom. An atom is 10 to minus 1 nanometers. So that's 10,000 less, actually, than that hair. So you use light, and light has these long wavelengths. You can't do anything with it. It will wash out everything, because it bounces all over the place, and you won't see anything. So what could you do to visualize, for example, atoms? No, you use electrons. And electrons are charged, which is very nice. So that means you can focus them. Electrostatically, you can focus them because they have charge. And you can accelerate them to certain energies. And you can make it the energy that you want in order to see what you want to see. So you bounce these electrons off your atoms, and you can visualize the atoms, because the wavelengths and the size of the object, the atom, matches. And if you look here at this is not a very sophisticated photo, but I like this is a gold foil. And you have a gold foil, you pull on one side and you pull on the other side, and you look how that gold foil separates and how it's held together by strings of atoms. So we're pulling here, and we're pulling here, and so you see there's a string of atoms. There's 1, 2, 3, 4, 5 strings. Can you see them up there? Yeah, 1, 2, 3, 4, 5, okay? Now, you pull harder, one string goes away. This is a row of atoms here. You pull further, you have 3 left, you have 2 left, you have 1 row of atoms left, and there you have pulled it apart. It's not, no, you have 2 separate pieces. So you can, on an atomistic scale, you have seen how this gold piece is torn. Of course, we have much better microscopes now, and you can see the atom very sharply and very clearly, but I think it's a nice example. So this is about 12 years old. That field has progressed unbelievably. And so eventually I put a newer picture in there. But it really proves the point just. So we have a sodium atom, and we know the sodium atom at 80 degree Kelvin has a certain velocity, because temperature and velocity is directly related, okay? And if I can calculate the momentum for this. Now, if I have that sodium atom going into this direction, it has a forward momentum in this direction, and now I use light, photons, and I hit this with light. And the photons have a momentum. And if I give it enough momentum to counteract this, that means this has a negative sign and this has a positive sign, I add the momenta up, hypothetically, I would be able to stop that sodium atom. Because if I have enough light hitting here with the right momenta, then I will stop it. So this is what we are doing. And we use light of 600 nanometers. And I'm asking you now, how many photons of that 600 nanometer light do you need to stop that sodium atom? You cannot completely stop it because that's impossible, but let's assume we stop it, one-on-one, okay? So that's the question I pose to you. Is it 1 photon, 100 photon, or 10,000 photons? Why don't you think about this and give me your answer? So there's some of the information is here in this board that you will need. So and h is a constant. You don't have to use h. You use it as a constant, okay? Don't put it in your calculation times 10 to the minus 23. Both of them have that constant. But it's written in the denominator. See, there is some need for a clarification, obviously. But you already found out that 1 photon is not going to do it, okay? Because you can calculate the momentum. The momentum is what? The momentum is, we have here the wavelengths. Here we have the wavelengths for that here, okay? And the momentum is, for this here is then h divided by the wavelengths. So you know the momentum of the sodium atom, okay? Now, you can calculate the momentum of 1 photon at that wavelength. And then look at the equation and see how many of these photons you need to get equal to that. Why don't you discuss this with each other, and we'll see what you come up with. So what is it? And you're sure about that? Good. Excellent. Okay, don't forget to click in. We are counting now. Can click in at any time. Just make sure that we have you. So there is a midterm Monday in a week. Okay? So Thursdays there's a review session from 5 to 7 here. So let's have a look at this. That's not... Yeah, this is excellent. So very good. So somebody could convince somebody and somebody understood something. Okay? So this is 86%. This is what I like to see. So the solution is as follows. We know the sodium atom here, the wavelength is 0.06 and the wavelength is here 600 nanometers. Okay? Now, the momentum is h divided by the wavelength. So the momentum for this is h divided by 0.06. So this momentum has to equal this momentum. But that's not it. That momentum is h divided by 600. So how many photons you need to match this here? That's in the denominator, remember? Okay? You need 10,000. H divided by 600 times 10,000 gives you exactly that momentum. And with this, you can stop this moving particle and you get to absolute zero temperature. If you do that, you let me know because you win the Nobel Prize. Okay? And you push everything that we know so far about thermodynamics becomes invalid. It's not going to happen. Okay? The lowest temperature that people are getting, they used to be in microkelvin. In 1987, a relatively young physics professor, his name is Stephen Chu, he won the Nobel Prize for this. He did exactly something like this. He stopped them with light. But he only stopped them to a certain velocity, which related to a temperature of tens of millions of degrees. That cold. But now they can go to picokelvin. I just looked it up today. The world record is 0.25 picokelvin. So this is micro, nano, pico, 10 to minus 12. 0.25 times 10 to minus 12 Kelvin. But they will never, ever get to absolute zero. Okay? So, and this gentleman, Stephen Chu, he used to be the director of the Lawrence Berkeley Lab, where I also have worked. And guess where he is now? Stephen Chu. He's our Secretary of Energy. He got his PhD here. He worked in Stanford. And he came back. He's seen the light. Okay? And then he went to government. I'm not so sure about the light, though. But, and no pun intended, he worked with light. So the answer was 10 to the 4. All right? So now let me ask you that. The kinetic energy of a moving particle is 1/2 the mass times its velocity squared. So the kinetic energy is actually the momentum squared divided by 2m. If the particle was the same, you can sort of forget this part here. Okay? Just helping you to solve that. So we have electrons, and we treat electrons as waves. We have electrons with a wavelength of 4 nanometer. And they are heated so that their kinetic energy goes up by a factor of 4. So that their kinetic energy increases times 4. What is the new wavelength? Why don't you think about this? So we start out with 4 nanometers. Could it be 8? If you increase the energy? Let's think about it. I hope you don't vote for 8. Because everything I say is totally useless. No, actually, it's not useless. You just didn't hear what I said, that's all. Not today, but earlier. If you increase the energy, does the wavelength increase or decrease? Does what? Decrease, okay, good. So now we are down to 2 answers. 50-50 chance. Would you like to phone somebody? So you quadruple the energy of the particle, what happens to its wavelengths? Yeah, that's about to be expected, about 50-50. All right. So how can I explain that to you? Let's see. The kinetic energy and the momentum are related, directly related. If the kinetic energy goes up, the momentum goes up exponentially. What is the exponent? That's the first question. If you find out the exponent, then you can answer that question. Why don't you discuss this with each other and come up with a good solution? Preferably with the right one. This is the relation that you need. Okay. Yeah, we're getting there. That's excellent. So learning, that's what I like to see. Let me go back here. So you have your equation here. If the kinetic energy goes up by 4, how much does the momentum go up? Doubles, exactly. Okay. So this is the kinetic energy. This is your relation between the kinetic energy and the momentum. The m and the factor 2 as a constant. So 4 times the kinetic energy is 2 times the momentum squared. All right? So with this, you can put that in here. So there's 2p in here now. And with this, your wavelength gets 1/2. All right? And 1/2 of 4 is 2. And 8, of course, we have ruled out because if the energy increases, the wavelength has to decrease. Okay? All right, we have talked about waves, and we are now talking about waves and the electron, and we have talked about this. Now let's see about some properties of waves and how this relates to energy, and then how it relates to the electron. So you all did these wonderful experiments. You jumped ropes at one time, or did skipper rope, or whatever it's called, or doper rope, or whatever, and rope-a-dope. So my wife would be mad at me. She said, you can't say these things. It's also... anyhow, so we have following. We have a rope here. So is this a wave? No. So the energy of this is 0. Absolutely 0. It's 0, the energy of this. Okay? As a wave. Now, but I know an electron is a wave, and it can't have 0 energy because it moves around the nucleus. So my condition is that the wave function has to be 0 here and has to be 0 where Karen holds it. Okay? That's the condition we put on that wave. And I explain to you in a little while why we put this condition on there. So let's see what the lowest energy state of that wave would be. Is this a wavelength? It's half a wavelength. It's one lobe. A full wavelength has two lobes. So she uses not a whole lot of energy to do that. Why don't you put a little bit more energy into that? So we have now, do we have a full wavelength? There's a node here. It is not zero, it goes through zero. Right here it goes through zero. Should be standing. And there's one lobe and there's another lobe. When this is up, this is down and vice versa. One full wavelength. So did Karen use more energy? Obviously. That must be a higher energy state. Now let's see how many Karen can do. I can see it so well. Let me know how many lobes you see, okay? And how many nodes, all right? Let's go for it, Karen. 1, 2, 3, 4. So this is 2 full wavelengths. 1, 2, 4 nodes, and that means 4 lobes. Excellent, thank you. Did you see how much energy she had to put in there? So this is definitely a higher energy state, because we need a lot more energy to do that. And this is exactly what the electron does around the nucleus. So we have a state, and this is quantized. It's not a quarter of a lobe, it's not an eighth of a lobe, it's half a lobe. Okay? It's half a lobe, it's 1 lobe, it can be 1.5, it can be 2 lobes, 2.5, 3, and so on and so on. Okay? But it can be 2 1/4, then it wouldn't work, because it has to be 0 here and it has to be 0 there. So you see in the energy of an electron in its ground state, it still has energy, but it's the lowest possible energy state, which we give a quantum number. And we say that lowest possible energy state we call quantum number, we give it quantum number 1. Okay? So that's the ground state of that energy, of that electron. An electron cannot have a lower energy than its ground state. So these are quantized states. It goes from one state to the next state, to the next state, to the next state. Okay? So this is what we have seen. This is our wave function in one direction. It had one lobe. It had the lowest possible energy. We make this here. This is the energy here. We do this as an energy scale. The energy increases here from a certain energy, not 0, from a certain energy up to increasing in energy. So this is the ground state, and we call this n equals 1. Did you see any nodes there where it went to 0? No. So it has 0 nodes. N equals 1, 0 nodes, ground state. Now we're going to give energy to that electron. And we can only put it in a certain other quantized state. And this would be the next state. So what would it have? It would have 2 lobes, a full wavelength. So you have a positive lobe and a negative lobe, and here's the node. So that would be the energy here. It's higher than that energy. That would be the quantum number 2, and it has 1 node. So these energy states and nodes and quantum numbers are related. So they tell you if you have quantum number 2 compared to quantum number 1, that quantum number 2 is a higher energy state than quantum number 1. So now we keep going. Quantum number 3 has 1.5 wavelengths, 1, 2, 3 lobes, 2 nodes. This is the energy. It's higher than these energies below here. N equals 3, quantum number 3, and 2 nodes. So we can characterize this state first, and we say, this is n equals 3. And with this, we know the energy. We can describe the energy. We don't know. We can describe the energy of that electron around the nucleus. Now, sound is also quantized. It's not a condition. It doesn't go like this. Sound is quantized. You have here, we restrict the sound to this tube. The wave function has to be here 0, and here 0. It can't go out of the tube. It has to be in that tube in order to make a sound. Goes back and forth and back and forth. So now I'm going to start. You don't hear anything because the sound is so low. You see, it went up, 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 down, 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 down. Okay? It didn't go. It went. Okay? So it's quantized because that wave, only certain standing waves, these are called standing waves, certain standing waves fit in here. Okay? That's the same thing than this. All right? So now let's think a little bit more about this. So that wave, of course, goes around the electron, around the nucleus. That electron goes around the nucleus. So it's not going to go back and forth like here in this room. So this is why we had these boundary conditions that a wave function had to be here 0 and had to be 0 here. Because if we take that rope off the wall and put it together, then the wave goes around the nucleus. And it has to meet here. That's why it has to be 0. If you look at this here, it can't be n 4 1/3. Then it will not meet that wave, or n a fraction of that. Yeah? Can be of half, can be n equals 1, n equals 2, n equals 4, n equals 5, and so on. So that's why the boundary condition on this experiment has to be 0. Okay? This end and that end. Because just take that rope off here as it is swinging, and now put it together. And now you have that electronic wave going around the nucleus. Doesn't go necessarily in a circle, like it's depicted here. This is just for one specific condition. And so this is a higher energy state than this. You can excite that electron into a higher energy state. How do I do this? So now we understand this would be the ground state of an electron. And that electron is in an atomic system. It is bound within the atom. And so we can do spectroscopy with it. We can do absorption spectroscopy. We give it light. And now I use visible light from red to blue. And I use that wavelength here, that purple. There is no way that this energy fits any of these spacings here. These are given spacings, given energy spacings. So that energy is delta, E is h times nu, but there is no difference between them. So I can't do anything with it. It's not going to pick anything up. Because this electronic system has certain energy levels. And these energy levels are different for each electronic system, of course. So now let's see. Blue had the right wavelengths. It fit right into that space, that energy space. Delta E is h times nu, and nu was the frequency of the blue light. So this atom absorbs blue light. It takes that electron from n equals 1 to n equals 4. 2, 3, 4. So it takes it up, kicks it up in energy, and you have what we call an excited state. And this is the first excited, second, third excited state it would be. And so you see, it fit the difference in energy is this energy minus this energy, delta H. Okay? And this is exactly that wavelength. So what you see in your spectrum, this absorbs it. It's missing in your spectrum. That wavelength is missing. So let's see if we do another one. These are called electronic transitions. Now this green here doesn't fit. Now we're going to go to lower energy, and you see that this green here fit. It goes from n equals 1 to n equals 3. So that's a less energy difference than this, because the wavelength itself is less energetic. So this fits. So it comes in quantum. This has to fit the energy that you put into that atomic electronic system, has to fit the electrons to get into these individual electronic levels. And these electronic levels are different for different atoms. So now this yellow, nothing happens. Now, but red has not that much energy. but it's exactly that wavelengths that we needed here to get from N1 to N2, okay? And you see this is missing in your spectrum. You can do this also in terms of emission spectrum. Now, if the light gets excited, if the electronic system gets excited, so an electron gets from a lower energy state into a higher energy state. Now it's excited, it has extra energy. Now it can go down again and give off that energy. That's called an emission spectrum. So first you excite it, and then you see the emission of that energy. So this would be, what would be the emission? The highest energy emission would be the blue one. So it goes back from this to the ground state, from here to here. It emits blue light, because that's the energy of the blue light. H equals h times nu, the frequency of that blue light. Now this one, and you see an emission spectrum emits that blue line here. If you have the green light, it's lower energy. It goes from n equals 3 to n equals 1. And you see if this is our energy scale here, or our frequency scale, or no, our wavelength scale, I'm sorry, it's the wavelength scale. So it emits green light. That's an emission source. Nothing else. Emits blue light, green light, and what else? And red light. That's characteristic for that atom. That atom emits green light, blue light, green light, and red light. And it's not the atom that emits. Yeah, go ahead, sir. It doesn't fit. Yeah? If the energy level 2 is what? No, it has to be whole numbers. It has to be whole numbers. That's the whole point of quantization. It has to be whole number. There's only N1, 2, 3, 4, 5. There's no N2.5 and no N3.5 and no N3.375. Okay? Because otherwise the wave function doesn't fit. It can only be? Yes, it can be. The distance is an energy. That's a fixed energy. It's a quantized amount of energy which is related to that wave function of that electron. There are only certain energetic conditions that will fit for that electronic system. So, and we're going to do some exercise about this. This will be the question that we start next time with this. We have an energy level scheme and an emission spectrum. And wait, we are not done. We have an energy level scheme and an emission spectrum, and if I go from 3 to 1, I want to know if this is your wavelength, this is your frequency. Do you see line A, B, or C? Think about it, and we'll start with this on Monday. See you on Monday. Thank you.